So we are tasked with creating a Sallen Key circuit, Sallen Key filter with a damping ratio between 0.1 to 0.1 to 0.3, a cutoff frequency along with a cutoff frequency of between 500 hertz and 500 hertz and 1500 hertz. And last last is a gain between 0.2 and here between 0.2 and 2. So this is what we're given. So next we have to find out the values for our components in the circuit. And luckily we're given a website that can find out all these values for you. So we figured out that our first resistor will be 13 kilo ohms, our second resistor will be 5.6 kilo ohms, our first capacitor will be equal to 0.1 microfarads, and then our second capacitor will be equal to 0.0033 microfarads. Along with these component values, we also have a cutoff frequency of 1026.827. Yeah, at this cutoff frequency, so it's in between, it's in the range that we were given. And then also we have a Q factor of 2.525, 1999. Yeah. Okay, that's our Q factor. And then last is, oh no, not last. Next we have our damping ratio, and this is 0.198041. And then we have our gain. Our gain, oh, sorry. Next is our phase margin, and this will be 32.6 degrees at frequency 1394.1 hertz. And then last is our gain. This will be equal to 1. So these are all our component values. And next I will I'll show a circuit diagram of the Sallen Key filter. So we start off with our resistor, two resistors in series going into the op amp. And then in the feedback, we have a capacitor. This will be C1. So everything has to be perfect. And then we have our C2 ground. And then, yeah, so that's our two resistors and two capacitors along with the op amp. And then this will just be V out, stable V out and V in. I got R1, R2, C1, C2. Perfect. So next, after showing this is the circuit diagram, actually the transfer function of the circuit. So obviously the transfer function is V out over V in, and then this turns out to be, I'll just do it in the components first. There's no values. Just change them. Yeah. Yeah, so transfer function out over V in. And this ends up equaling we equal to 1 over R1 C1 R2 C2, and that'll be all over. So that's equals to V out and then V in. So S squared plus S 1 over R2 C1 plus R1 C1, and then plus 1 over. Then it's just 1 over R1 C1 R2 C2. And then when you sub in the values for these components, you'll get um you'll get this. So on the top, you'll get 416250. Get this value at the top, and for the bottom, it will be S squared plus 255 for 2554 point 1.94. Yeah, so you get this one, and then plus obviously 41625041 at the end. So after we've figured out the transfer function, we can move on to finding the B and A coefficients. So the top, the numerator will be B, and the denominator will be A. It's just me trying to figure out how to change the color of the pen. Yeah, yeah, perfect. So I'll just label it out here. You got B and A. So so A0, this should actually be A2. So A2 equals 1. A1 equals the middle number there, 2554.945. And then you got, yes, I feel like I made a mistake here. I know. Yeah, so A2 and then A0 will be 416.25041. So they're the A and B coefficients. And this will be for for when we use Matlab, and then V0 will be that, and then that's all the calculations that we did. Yeah, there you go.
Right, so this is where we're going to be using our step response to get our frequency response. So just go ahead and load in our step response. Just using audio read. So files go step 3. So load that in. One of the steps along the way is to derive this. So we use the diff function in Matlab. So we obviously want our cross to be in hertz and not bins. So we'll just take that into account. So on there is going to help us do that. And then we'll just get the FFT of that. And we'll go on ahead and plot it then. So save and then run. So now we can see that we've gotten our frequency response, and yeah, shows it pretty well. We can see all the negative frequencies there on the right hand side, and then kind of from the 8,000 down is our actual frequency response that we're concerned with in this case. So yeah, right. So what we're going to do here is we're going to apply the frequency response to just some random signal and see what we get out. So we did this using LTspice. This is random forest with noise, and then we're plotting the FFT of the input and then the output. So if we go into Matlab, we've got it set up here already. So what we're doing is plot the FFT of signal. Okay, and then we save. So here we get our figure, and we can see that our frequency response is applied, and yeah, we're completely missing these higher frequencies. Just do note the change in axes changing the scale on the axes as well. Yeah, that's all. Okay, so in this part I'm going to be showing the A and B coefficients and what we can use them for in Matlab. So I'll just set up my A coefficients here. And then my B coefficients also. So then be able to get the transfer function quite easily. So if I go ahead and run that, save it first. So you can see that I was able to get the transfer function quite easy. So furthermore, what we can do is we can get the frequency response to this by just going plot FFT and then the step response of this. Sorry, the derivative of the step response of this. So then if I go ahead and run that again, I'm going to see here that the frequency response shows up. So yeah, just one other thing I can do is I can actually get a Bode plot of that. So I can go Bode and then sys1. A second. There we go. So we can see our phase here and then also our magnitude. So yeah, all right, that's all. Right, so now we're going to create the Sallen Key circuit. So start off, place the resistors down, R1 and R2. Follow this up with the op amp, this universal one here. So I'm just going to hook them up like so. Don't forget a voltage source as well. For this, this is what we're going to use to get the step, to generate the step even. And ground that also. Now, just going to put in the capacitors. C1 here, and C2 is just going to go down here. Again, just hook that up. Just like so. And then just pair the op amp also. goes around. And the ground also. So looks like that's everything. So now I'll just have to put in the values. Final thing is actually just to put in feedback. Turn on and ready. So yep, that's the LTspice. Okay, so now I've just subbed in all my values for the capacitor and the resistors. And so what I've done for the source here is I've sent a pulse through, and for this pulse you can see this long number here. That's the amount of time it takes to change to its max value. So if we go ahead and simulate this, run it there, I'm going to compare the input, which is a step, and then the output, which is our step response. So you can see here that we've got our step response of the circuit. So yeah.
Here is a video of the final circuit being made. Here we have our step response along with 4 input and output sinusoids shown at 4 key frequencies, and this is on the oscilloscope.